the third argument? Is it there? No idea. I cannot tell. I can assume that this function accepts 3 arguments, but maybe not. Maybe only 2. Maybe the rest was just generated by the compiler, and it happens like this. If you take the example on the right, again, it's very difficult to say. Apparently, it takes 3 arguments. They are all on the stack, but we don't know if it expects anything in the register. Your temptation would say, okay, no problems. What about solving this problem by looking at the called function? First of all, you don't have the called function all the time. You see that we have indirect calls here. But even if you have a direct call, it's not that simple. I don't have a specific example here, but it's not always possible to tell if a function uses, your first naive approach would say, okay, if the function uses a register, then it must be an input argument, right? But what if the register is saved on the stack at the beginning? Is it a use or not? Maybe it's just saved until it will be restored at the end. Maybe it will be restored in the middle of the function, so you cannot tell. Most of the cases you can solve, no problem. Most of the cases, let's say 99% of the function, you get it right. But one function in the output is wrong. And this function, unfortunately, gets called from 200 places. So your output is plain wrong. Another example about return values. The example on the left. What does it return? Usually we know that the return value is in EIX. And we say, okay, we know that EIX. But what about EDX? Do we return something there or not? Again, based on my experience, I would say no, it doesn't, because we subtract EDX from EX. It's highly unusual that the function returns both registers in this case. But maybe I'm wrong. To the left, the same problem. EDX, is it returned or not? We don't know. Well, based on the experience, we can say something, but it's mostly artificial intelligence stuff and things like that. Yes, I have a slide about the input arguments. So the naive assumption that if a register is used, it must be an input argument, it's wrong, because it may be accessed, read, to save its value, and after you will restore it at the end. To allocate stack frame, on the right, we have push ECX at the very beginning of the function. What happens here? Do we use ECX? Maybe not. Maybe we just allocate stack. As a human being, you also have all these problems, but you kind of solve them one way or another as soon as you encounter them. So it goes like this, and sometimes you see, okay, I made the wrong assumption, and you go back and you correct things, and so things work well. By the way, on the left, it's even more interesting example. You see that we use EDX. For if you have a formal approach, you would say, okay, we have EDX, we use it. The high bits of EDX are used, but it's just an appearance. In reality, the function does not use EDX, the EDX register here. Indirect access is a problem because you have pointer alias problem. You don't know the precise object boundaries. Again, just a small example. We take the value of a memory cell, arc8, and we put it into ESI. And after we do that, we do this, we do that, and after we use ESI. Pedantic, strict approach would be to generate the code on the left. This way, we don't lose anything. We are correct. We generate correct code. It's correct, but it's kind of ugly. It's not optimal. And any human being and many users already complain why we don't put arc8 right into the call statement, like it's done on the right. You see that we have only 2 lines. Having 2 lines instead of 3 lines is much better. We have 30% of gain. Less code to read, less code to analyze, everything is better. But unfortunately, the decompiler cannot do it for you because the decompiler cannot prove that between the moment we move the value into the register and the moment we use the register, the arc8 is not changed. It can prove about ESI, taking some assumptions, making some assumptions, but it cannot prove for the memory cell. Just impossible. Indirect jumps are also a problem. Okay, I think that I will skip this slide. You understand that we have to solve indirect jumps as well, but they are not easy to solve. And problems. I will stop here because there are too many of them. So everything here can be proven that just impossible to solve the problem in generic case. So we have a kind of hopeless situation. Yes and no. We can restrict ourselves to something very specific from at the beginning. Let's say we start with a simple, under quotes, case. We'll handle only compiler-generated code. So we don't have a hostile adversary human being. We'll handle only 32-bit code, and no floating point, no exceptions, nothing. Something simple, something basic. And we will have the following assumptions and the kind of basic ideas how to build the decompiler. First of all, the decompiler will be configurable. The user will be able to specify the calling conventions, the stack frame sizes, the memory model, and other stuff. The decompiler will use sound theoretical approach to all solvable problems. For example, data flow analysis on registers, we can prove things because registers, they don't have indirect access. The biggest problem is indirect access. When you have pointers to somewhere, you don't know where it points to. Potentially, it can point to any place, and it spoils many things. For the cases we cannot prove anything, then we will use some heuristic approach. Indirect jumps, function prolog and epilogs, call arguments, the problems I showed you, we'll just make some rules that will work, let's say, 95% of the time. 5% of the time, they won't work. Okay, we know it in advance. That's why we say our decompiler will be interactive. So the user can go and say, change something, specify something, so to kind of direct the decompiler and to change the output. Of course, we'll prefer to generate ugly but correct output rather than nice but incorrect code. And that's all, yes. And the user will be able to specify what to do in difficult cases, or when the information is not available, the user will provide it. In fact, it's the same philosophy as with IDA. Why IDA is so powerful? Because IDA relies on you. You, as a human being, as an analyst, you can tell IDA that here it's code, you stupid tool, you don't understand this, you make it code here. And you gave names, nice names, you annotate the listing. The decompiler works exactly the same place, the same way. So if you expect something that you press a button and you have something, no, it will not work. For me, it was natural to have the following architecture. So at the bottom, we have a disassembler. My choice was IDA Pro, of course, that reads the input file, it decodes instructions, and creates function for us. So the function division is done, which is good. Using IDA Pro is good here as well, because even to separate functions from, to create nice functions, it's again a very difficult task, and very difficult to solve in a general case. So that's why, again, the user can go and say, okay, this here I have a function starting here, ending there. The next, on top of the assembler, will be a generator that will generate a microcode. The microcode is the name of the intermediate representation, intermediate language used by the decompiler. So we move away from the processor-specific stuff as soon as possible, and we switch to this microcode. And this step, this layer will also handle all platform-specific aspects. And the kernel is the core of the decompilers that will do everything that we need, do decompilation. And on top of this, there will be also add-ons like plugins, visualizers, other tools, and so on, so on, so on. And the decompiler would work using the following phases. So first of all, we generate microcode. At the same step, we also analyze the function prologue, switch instructions, verify that the function is defined correctly, that it's not like a stray move instruction, because this is not a good function. A good function must end with a return or exit or something that makes sense. The next step is to optimize basic blocks one by one, simplify instructions and other stuff. The next step is to analyze everything globally. There we perform data flow analysis and delete dead code and other stuff. Then we allocate registers, allocate local variables. In fact, we replace registers by local variables. And after that, we have the remaining steps. We do something called structural analysis. We try to extract the control structures like while, if, switch, and other things that you use in high-level languages. And after that, we can generate code, pseudocode. I call it pseudocode because calling it C, C++, C would be, it's C in fact. But I call it pseudocode just to avoid any questions. Why does it recompile? Why it doesn't do this? And it's a pseudocode. I don't care about recompilation. My goal, as with IDA, is not to recompile things, but to make easy for you to understand things. So you look at the code and you understand things. The initial pseudocode that we generate is really bad. It's ugly. I will show you. So we need to transform it. And there are around 150 maybe different rules. Oh no, less than that. I don't remember the exact number, but anyway, that make it better. Like kind of, these are code transformations that do not change anything. No semantic changes, nothing changes, but they still make better. And at the end, I do type analysis. By the way, this is something that I do. The other steps, you can say that microcode generation, you can find similar steps in other decompilers. But the type analysis, they always do it at the beginning, at the very early stages. I think that it's a very big misconception. The type analysis is possible only at the end, not at the beginning. Because only at the end you have enough information to derive type information, to build type equations and to solve them. And there's a final touch that to rename variables so they look nice and other stuff. That's the final step. I will just show some slides to you so you see how they look in my development system. In the final product, you don't have this microcode. Everything is hidden for the moment because the reason is that I don't know if the microcode will stay the same. Maybe it will change. Maybe, for the moment, it doesn't support floating point, for example. I have to add floating point, so it will change. Microcode as generated is huge because every instruction is translated into a sequence of micro instructions. Some instructions are skipped. For example, the first push ASI is skipped there. It belongs to the prologue, so we don't generate it. The first move is translated directly to move, but if you take the last instruction, like jump 0, you will see that it's the last, how many? 3 instructions use this, the last 3 micro instructions correspond to jump 0, the last 3. So you see we take the code segment, we put it into a temporary register called seg, we put the an offset, we put it into another temporary register, and after we say jump if 0 flag, then we jump to this address. This is quite